in our intuition, time is an abstract concept that exists independently. It has only one direction, flowing continuously from the past to the future. But have you ever wondered why that is? Why time can only go forward and not backward? Why we can only remember the past and not the future? Are we in time, or is time in us? Welcome to Audible Wisdom. The book we're going to read today is The Order of Time. This book will take us on a journey to explore the nature of time and turn our preconceived notions of it upside down. The author of the book, Carlo Rovelli, is an Italian physicist and one of the pioneers of the circle theory of quantum gravity. He has been called the next Stephen Hawking. We are going to go through this book in 3 parts. First, we'll look at the truth about time from both the macro and micro levels. Second, we will enter a world without time and see how everything works without the command of time. Third, we will explore why we can still truly feel time in a world where time does not exist. We will begin our journey to find the truth about time. 1. The truth of time at macro and micro levels. Let's start with the macro perspective. In our impression, time gives us the most intuitive feeling. Our most intuitive sense of time is that it is characterized by independence, unity, immediacy, and direction. However, recent discoveries in physics have overturned these views. Independence of time. Let's begin with the independence of time. It is a common belief that time is independent and that nothing can stop it. This view was first expressed by Isaac Newton. Newton believed that time is absolutely independent and has no connection to anything outside of it. He used this view of time as the basis for modern physics. Today, we have taken this view as common sense, but it is not. The fact that time is independent and unstoppable is only Newton's personal view. It's not an intuition that mankind has had since the beginning of time. Some philosophers also disagreed. The ancient Greek philosopher Aristotle is a typical example. He was the first known person to ask what time was. This was almost 2,000 years before Newton. According to Aristotle, time is a measure of change. In other words, when we talk about time, we're really talking about things that change. For example, I have to go on a business trip for 3 days. 3 days means that between the time we leave and the time we come back, the sun will go around the sky 3 times. If everything stayed the same, would time stop? Aristotle's answer is yes. If everything stayed the same, there would be no time. For time is merely a record of change. If this is the case, then why is it that even when we close our eyes and lie still in the darkness of the night, we can feel the passage of time in silence? It is because your heart is moving and your thoughts are changing, so you can still feel time. This idea that time must exist according to change is the opposite of Newton. In contrast to Newton, there was Leibniz, a German mathematician who lived at the same time as Newton. He also believed that time cannot exist independently. Behind time, there is something more fundamental, a cause and effect relationship. For example, if there is a glass of beer on the table, there are many hidden causal relationships. If you don't open the bottle of beer, you can't pour it. If the beer is not poured out, the glass will not be filled. So by sorting out cause and effect relationships, we can understand the chronology of events. For Leibniz, time is like a domino, a transmission of cause and effect. When the first domino falls, it affects the second domino. The second card affects the third domino, and one by one the dominoes fall. When we feel the transmission of cause and effect, we feel the passage of time. Leibniz strongly defended his view of time. It is said that his name originally had the letter T in it. In Newtonian physics, T stands for time. Leibniz firmly believed that Newton's absolute time T did not exist. To be consistent with his beliefs, he dropped the letter T from his name. So is time independent or not? Einstein made the final judgment that time does not exist independently. Let's look at how Einstein proved it. First, he established the principle that the speed of light is constant. That is, the speed of light is the same for every observer. It doesn't matter if you're standing still or on a spaceship, you see the same speed of light. In the narrow sense of relativity, going beyond the speed of light is not allowed, which circumvents Leibniz's point. Why is that? Imagine someone on the other side of the room sending you a faster-than-light message on their cell phone. You get the message before you see the other person pull out their phone. That's a problem. The cause and effect is broken. Once you allow faster-than-light situations to happen, all sorts of absurd scenarios occur. We can see that. The glass breaks before it hits the ground. We see the victim die before the killer shoots him, and so on. It is for this reason that Einstein's narrow theory of relativity establishes the principle that the speed of light is unchanging. With this assumption, all causal relationships in the world are not reversed. This sidestep preserves Leibniz's view of time. Secondly, Einstein proposed a new view of time and space. Earlier, Einstein mentioned that the speed of light is unchanging. It is only this fast. The space of the universe is so large that it takes time for light to travel from one place to another. The greater the distance, the greater the time difference. Therefore, time and space are closely related and inseparable. The most intuitive example of this is the light year, which we use to measure cosmic space. We use the concept of time as a unit of distance. This implies that time and space are inseparable. We then unify them into a whole called space-time. Einstein not only unified time and space, but also gravity. For example, the gravitational pull of the sun causes the Earth to rotate. It's actually the sun's enormous mass that bends the space around it, and the Earth just slides along with the curved space. This curvature of space acts as a gravitational field. Space and time are two sides of the same coin. So space-time is the gravitational field, and the gravitational field is space-time. A field is a physical entity. A gravitational field, like an electromagnetic field, is independent of us. Although it is independent of us, it is definitely not beyond the object. Therefore, the field is related to the change of things. It is dynamic. Let's take an analogy. According to Newton, time is like a stage. Life and matter in the universe are like the actors on the stage. No matter how the actors perform, time, the stage, remains motionless. But in Einstein's view of time, the stage is always performing with the actors. Its performance changes according to the actors on the stage, and the absolute independence of time is broken. How does the stage of time perform? The unity of time. This brings us to the second characteristic of time, its unity. It is widely believed that the unity of time means that all people are equal before time. Time is perceived by the whole world as uniform and fair. But the truth is just the opposite. Time is never fair. Its true nature is to fluctuate between fast and slow. There are two factors that affect the speed of time: quality and speed. Let's start with mass. An object slows down time around it, and the greater the mass, the more noticeable the slowdown. This is because the gravitational pull of a massive object can distort the surrounding space-time. The greater the mass, the greater the distortion. The Earth is a massive object, and the closer you get to the center of the Earth, the slower time passes. Therefore, people who live on the plains age more slowly than those who live on the mountaintops. Even if the difference in altitude is only a few centimeters, this miraculous effect still exists. In other words, the cells in the feet age more slowly than the cells in the head. Then there's speed. Exercise also slows time. Time on a high-speed train is slower than time on a bicycle. The faster the speed, the slower the time. Why is that? Let's do an experiment. Imagine there is a photon clock with a simple structure and two mirrors, one in the middle and one in the other. In the center, there is a photon that bounces vertically between the mirrors. The technology uses the number of round trips it makes to measure time. On the ground, suppose the two mirrors are 1 meter apart. Then the photon makes nearly 1.5 billion round trips between the mirrors to complete 1 second. Now, if you put this photon clock on a high-speed spaceship, what will happen? The people on the spaceship see the clock moving vertically up and down. But for you outside the spaceship, you see something completely different. The photons themselves are moving up and down, and the ship is moving forward. When you put the two together, you see the photons moving diagonally. In other words, you're seeing the photon travel a longer distance. Since the speed of light is constant and the distance is longer, the time it takes for the photon to go back and forth is also longer. So in your eyes, time has slowed down on the spaceship, and everything seems to be in slow motion. The man on the spaceship sneezes in 1 second. But for you, it took him a minute to sneeze. Now we know that the flow of time is altered by mass and speed. People at different altitudes, in different modes of transportation, experience different times. So which time is real time? The book says, because there are so many times, none of them is more real than any other. In this way, we have reversed the second characteristic of time, unity. The present nature of time. How do two people at different times communicate and talk to each other? Now let's look at the third characteristic of time, presentness. An important concept in time is the present. If your family member is in the room and you want to know what he is doing, you can look at him. But be careful. The way you see your family is that you receive light from them into your eyes. It takes time for the light to reach you. A few nanoseconds, say, or a billionth of a second. So you're not seeing what he's doing now. You're seeing what he was doing a few nanoseconds ago. It's such a short period of time that we don't notice it. But what if your family lived 4 light years away on a neighboring planet? You'd see what he was doing 4 years ago, not what he's doing now. You might say, I'm seeing what he's doing now, for years later. But that doesn't work either. As we said, there is no uniformity of time in the universe. On Earth, for years have passed, but in the time of the family members on the neighboring planet, 10 or even 15 years may have passed. There is no moment in time on Proxima Centauri that corresponds to the present moment on Earth. Not only on Proxima Centauri, but in the entire universe. There is no unified time. The concept of time can only be localized. The concept of the present moment that we talk about on Earth is like a bubble of air around us. It is always just the present moment in our eyes. It does not extend to the whole universe. How far can that bubble extend? It depends on the precision with which we limit our time. The greater the precision, the smaller the bubble. The concept of now covers a narrower range. If we use nanoseconds, the present is defined as a few meters. In milliseconds, it is thousands of kilometers. Since it's hard for humans to tell the difference between a few tenths of a second, we think of the whole Earth as one bubble. So, the definition of now is a vague description based on our own feelings. It's like when we see a meeting point between a rainbow and a forest far away. But when we go to look for it, we find that it doesn't exist. In fact, these qualities do not have the greatest impact on our daily lives. Directionality of time, past to future. The fourth characteristic of time that we find most cruel and merciless is its directionality. For centuries, countless people have lamented the fact that time never returns. Why can time distinguish between the past and the future? Physics in the 19th and 20th centuries discussed this question. Although we think it's natural for time to flow from the past to the future, but in physics, it's basically impossible to find a law or an equation that distinguishes the past from the future. Whether it's Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, or Heisenberg's quantum mechanics, all of these equations describe physical phenomena that are reversible. That is to say, if something happens in one direction, they allow it to happen in the opposite direction. Take a planet, for example. You can calculate its future position and speed, or you can calculate its past position and speed backwards. Since both forward and backward are possible, why do we say that one direction is the past and the other direction is the future? The only law of physics that is irreversible is the second law of thermodynamics. It says that heat can only be transferred from a hot object to a cold object, not the other way around. It's the only law in physics that is irreversible in one direction. And heat is closely related to the direction of time. Anything that makes a difference between the past and the future involves heat. For example, when a rock hits the ground, mechanical energy is converted to heat, which slightly warms the earth and stops the rock from moving. If there were no heat involved, the rock would have been bouncing around forever and would not have stopped because of the law of conservation of energy. Life ages because the body generates heat. Bicycles age because of the heat generated by friction. We use our brains to think because thinking also generates heat in the brain. If you look at the passage of time, you will see that heat is involved. Heat is the only physical quantity associated with irreversible phenomena, and it also acts as time. So how does heat differentiate between the past and the future? If the universe had been in thermal equilibrium from the beginning, with the same temperature everywhere, and the universe hadn't changed, wouldn't there have been no flow of time? The answer to this question must be found within ourselves. The reason is that our view of the world is vague and incomplete. What does that mean? Take an example. There is a deck of cards where the first 26 cards are red and the last 26 cards are black. We call the arrangement of this deck orderly and special. Now let's shuffle the deck. After shuffling, the suit order of the cards is clubs, diamonds, spades, and hearts. Is this a different kind of order? We will find out when we look at all the details. Each arrangement is special. Each design is unique. They can all be called orderly. And that's how we look at the universe. The universe is like an oversized deck of playing cards. And our planet is just a tiny speck of dust in the universe. It only interacts with a very small part of the universe. So we can't see all the combinations in the deck. We can only see a small part of it, like a blind man feeling an elephant while ignoring the vast majority of it. Thus, we think that time must be moving from the past to the future, and we feel the flow of time at the same time. If we consider all the details of the universe, there is no arrangement that is more orderly, more special. So does the characteristic of the flow of time disappear? The answer is yes. That is, time does not necessarily flow in one direction. When all the details of the universe are taken into account, any arrangement of the universe can be considered an order, and the distinction between past and future disappears. Therefore, the flow of time may not be a characteristic of the universe, but rather it comes from our unique human perspective. Therefore, in the macrocosm, time is not a characteristic of the universe. In the macrocosm, time has no independence, unity, immediacy, or direction. Time as we know it has changed beyond recognition. In the microscopic quantum world, the universally recognized continuity and certainty of time will also be reversed. As we have said, space-time is a gravitational field, a physical entity. Physical entities in the microscopic world have quantum properties, and time is no exception. Quantum has a fundamental property called discreteness. This means that its energy does not change continuously, but can only take on a specific value. What happens if time is quantized? Suppose we use the most accurate clock to measure an extremely small period of time. We would find that the measured time is broken up into segments. Like a kangaroo jumping from one value to another, the continuity of time disappears. There's something even stranger. The quantum has an undetectable effect. It's in a state of superposition, and no one can pinpoint its position. You've probably heard of it, Schrödinger's cat. It's a famous thought experiment on quantum superposition. It involves putting a cat in a closed container with a small amount of radium and cyanide. There's a chance that the radium will decay. If the radium decays, it triggers a switch that breaks the cyanide bottle and kills the cat. If the laser does not decay, the cat lives. According to the theory of quantum mechanics, since the radioactive radium is in the superposition of two states, decayed and undecayed, the cat should be in the superposition of a dead cat and a living cat. This dead and alive cat is called Schrödinger's cat. If time is also superimposed, then an event can exist in both the past and the future. It's hard to imagine that this is how the quantum world works. Now, by analyzing the macro and micro worlds, we've lost a lot of the characteristics of time. The time we know so well is almost non-existent. 2. A world without time. Let's see how a world without time would work. In the year 1967, two American physicists discovered a fundamental equation of quantum gravity. There is really no time variable in this equation. Time disappeared, and at first no one could understand this equation. Even the discoverer himself couldn't understand it. Without time, is the world static and unchanging? But then it was realized that the disappearance of time in the fundamental equation did not mean that time would stand still. On the contrary, it means that change is universal without being directed by time. It does not describe how things change in time, but how they change in relation to each other. Take an example and you'll see. Galileo discovered that the beating of a pulse could be used to measure the time it took for a chandelier to swing. Then the pendulum was invented because the time of each swing of a chandelier was fixed. Next, doctors could use the pendulum to measure a patient's pulse. Do you realize that this became a cycle? Galileo used the pulse to measure the pendulum, and the doctor used the pendulum to measure the pulse. In fact, time is only a mediator. We never measure time itself. We never measure time itself. We only measure the pulse and the pendulum, and then we derive their variations in relation to each other. The so-called time is like the auxiliary line we draw for geometry. This line doesn't exist, but it helps us solve the problem. If we can find variables that are synchronized with each other, like the pendulum and the pulse, we can use their mutual changes to represent time. There is no need to pick one particular quantity from these variables and call it time. When we give up time, one thing becomes clear. The universe is made up of changing events. We used to think that the universe was made up of objects, but in fact all objects are just changing events. For example, a rock is not an object. It is a complex vibration of a quantum field. A cloud is not an object. It is the condensation of water vapor in the air. A family is not an object. It is a collection of feelings about events. A person is not an object. It is a complex process of food, information, language, and so on, in and out. In this universe of changing events, everything can play time, and this is how our world really works. But then the question arises, since there is no time in this world, why do we really feel the existence of time? Where does it come from? 3. Why is there time? Let's move on to the third part, where time comes from. Time comes from our memory. As we said before, it is heat that plays the role of time, and it leads to an important result, which is that it leaves traces. For example, when we write, we use the friction of the pen to heat the paper a little bit, which leaves a mark. We judge time by its marks. What is marked is called the past. That which leaves no trace is the future. In a world without heat, a pen can't leave a mark on paper, so we can't tell time. Our brain collects traces of the past and allows them to form memories. In addition, the brain can also combine scattered memories to predict the future. For example, if someone throws something at you, your hand moves to where the object will appear and catches it. This is the brain's judgment based on past impressions. The brain also tells us that if you plant seeds, you will get food. If we go out in the rain, we will get wet. If we see a cup fall to the ground and break, instead of 3 different signals, our brain produces only one. What we see is the whole process of the event, not just the moments. Just as when we listen to music, we hear the combination of notes, not the individual notes. If the brain can't connect them and stay in the present moment, how can we hear the beautiful music in that moment? So the time we feel is a coherent sense created by our brain. This idea is actually very old. The Roman thinker Augustine asked about the nature of time in his Confessions. He said, "When I measure time, I measure what exists in my mind at the moment, and time exists in us." The German philosophers Kant and Heidegger held the same view. They believe that time exists only in the human sphere and that it is shaped by our inner perceptions. The writer Proust was even more thorough. In the first volume of his In Search of Lost Time, he wrote that reality consists only of memories. Now we have finally discovered the truth of time. 4. Summarizing the truth of time. To summarize, the 6 commonly held characteristics of time do not exist. First, time does not exist independently. Second, the flow of time is altered by mass and velocity. People at different altitudes and in different modes of transportation experience time differently. Third, time is not immediate. What we call present may be past or future to others. Fourth, time moves from the past to the future, perhaps only from our unique human perspective. Fifth, in the microscopic quantum world, time is no longer continuous. 6. Even in the quantum world, time loses its certainty. A thing can exist in the past and the future at the same time. Then we enter a world where time does not exist and realize that all objects in the universe, such as a cloud or a piece of rock, can exist at the same time. All objects in the universe, like a cloud or a rock, are just events in flux. And finally, we have studied the nature of memory. We discovered that time is just a continuous sensation created for us by the brain. In 1955, Einstein said this after the death of a close friend. "He left this world before me, but that's okay. Anyone who believes in physics, as I do, knows that the distinction between past, present, and future is a persistent and enduring illusion." This is not an academic discussion of time, but rather a quote from Einstein's life experience. It goes deeper than physics itself. Time is created by us, and we are the creators of time. That's the end of the order of time for today. Thank you for listening to Audible Wisdom. If you found this episode useful, don't forget to share it with your family and friends. See you next time.